2 is asking us to determine the pH of each solution. So I have 2 solutions here. So I want the pH of each solution. So the pH of 0.17 ch3nh3i. And then I want the pH of 0.25 ki. Okay. So if I have this, I'm going to do, this is a 2-part question. So I'm going to do the first part here. So this is, I guess this is part A, you can say. And this part is asking us the pH of 0.17 ch3nh3i. So if we want to find the pH of this, I would have to actually break this guy first down, right? So I have ch3nh3i. This is going to dissociate into water, right? This is going to dissociate in water. Or it's going to ionize, sorry, not dissociate. It's going to ionize to form ch3nh3 plus this would be I minus, right? Plus our iodine here. And this here, and we don't really, this step isn't in equilibrium, but we care about this this ch3nh3, this methylamine cation here. So this guy is going to then react with water, and that's going to give us our equilibrium kind of reaction here. Plus H2O. It's going to give us what we have here is this H is going to be given to this H2O. So I have H3O plus again CH3 and H. Now it's 2 here, and these are all. This is all an aqueous solution. So if I were to write the states, I could write the states as well. AQ, and this is AQ as well. So basically here I have my again methylamine. If I'm writing my equilibrium equation here, it's going to form my hydronium ion, and then I'm going to form my CH3NH2 here. My this here is the methylamine. So what I'm going to have to do is, again, I'm looking at my concentration here. I have 0.17 here, right? So if I have 0.17 molars, you can assume that I have, again, this is here was 0.17. This here could also be 0.17, which means if I did my ice table, this here is also 0.17 here. So my concentration of this cation here is 0.17 molars. And what we can do now is we need to find our KB of this solution here in order for us to solve for this equation here. So as you can see from the solution here, what we have here is they're doing an ice table like so, and they actually found a KB from databases. So let me just search it up and see if this KB is correct here. So give me a second here. So I'm gonna type in PKB of this is CH3NH2 here, and this is 3.3. I'm getting 3.36 or 3.32 here. Sorry, just give me a second. So I want to double check if that's right here. We're saying it's 3.35, so it's roughly 3.36. Okay, so I'll take 3.36 as our PKB here. So I'm going to use this as well. So if I did an ice table, so that's my ice table here, I can say that I'm starting with 0.17. The water does not matter in my equilibrium equation, and I started with 0 hydroniums and 0 of the CH3NH2, right? I'm going to minus some type of X. I'm going to add X and add X here, which means that in equilibrium I have 0.17 minus X here, and X here. So now what we can do is we can write our expression, right? And before we write our expression here, I'm going to assume that this PKB here is right. So this PKB is going to be of our CH3NH2, and this here is going to equal 3.36. So if I want to solve for the KB expression, all I'm going to have to do is I can follow this equation here. And let me do this in black actually, because it's not part of my ice table anymore. So if my PKB here is 3.36, then my KB is simply just 10 to the power of my negative KB here, which is 10 to the negative 3.36, which will equal take out my calculator here. 10 to the negative 3.36, which will give me 4.37 times 10 to the negative 4. So as stated here, which is great. 4.37 times 10 to the negative 4. This is our KB here. And now what we can do is we can write our equilibrium expression, right? I have my KB, and then I also have my concentrations here. So KB, I know it's going to equal the concentration of my hydronium times our concentration of our methylamine divided by our reactants here, which is the CH3 and H3 plus. And then, given this, I know that my concentrations of hydronium is X here. This guy is also X. And then, as found in my ICE table, this here is 0.17 minus X, right? So 0.17 minus X would be the concentration of my CH3NH3. And my KB here is simply just, my KB here, I actually, I can't use my KB here in this case because I'm actually making my hydronium ion, right? So I'm actually gonna have to find my Ka of this guy here. So this is actually a Ka expression, not a Kb expression here. So in order for me to find my Ka, I'm gonna have to relate it to Kw. So this is some side work here before we actually plug it into this guy here. So I know that Kw equals Ka times Kb, and Kw here is 1.0 times 10 to the negative 14 equals Ka times 4.37 times 10 to the negative 4, which means Ka here is going to equal, I'm simply just dividing 1 times 10 to the negative 14 divided by 4.374 here. So do that on my calculator. I'm going to get a value of 2.29 times 10 to the negative 11. And this here is actually going to be my Ka expression here. And as you can see, they did the exact same thing for Ka here, which is great. So I can say that my Ka here is 2.29 times 10 to the negative 11. 10 to the negative 11. And the reason why we have to use Ka and not the Kb here is because we're making hydronium ions, right? If we make hydronium ions here, we need to get our Ka of this expression here. So that's why I can't use Kb. If I use if it made hydroxide ions, what I can do is I can use the Kb here. But because I'm using making hydronium ions here, I'm forced to use the Ka here. So again, this here is my Ka expression. I'm going to use a small x approximation to get rid of this minus x here. I'm going to multiply both sides by 0.17. Times 0.17, I'm going to get a value of, this is 3.89 times 10 to the negative 12. And then I'm multiplying the x's here. I can square root both sides to get me, well, x here would be 1.97 times 10 to the negative 6. And this here will be my, concentration of my hydronium ions, right? This guy here is going to equal H3O plus, like as I said in my ICE table. And then now I can finally find the pH, right? And the pH here is simply just negative log of higher hydronium ions. And this pH will now equal negative log of this guy here, 1.97 times 10 to the negative 6 moles. This here is a mole, sorry. And this here is going to equal, simply just the calculator, negative log times 1.97 times 10 to the negative 6. And this will give us 5.71. So our pH of the first solution here is 5.71, and this here is our answer for 3A. And as you can see, this guy should be 5.71 here, yes. So pH here is 5.71, which is great. So this first solution here is correct. And finally for part B here, part B is different, right? I have a solution of pH of 0.1725 molars of Ki. I forgot the M here. This here is a molarity of Ki here. So let me write that down as well, of Ki. So this here is part B. So we solve for part A, which is 5.71, which is great. And part B is now asking us, we wanted 0.25 molars of potassium iodide here. And this here is an ionic substance, right? Ki here is an ionic substance, and I believe it is it's going to be a strong acid here. And the reason why I know this is because Ki here, it's going to dissociate into our K plus ion plus our I minus ion, right? And this here, and as you, I'm pretty sure, yes, they dissolves completely, right? Because it's an ionic substance for Ki. And then my HI here is going to then solve and then react with my water, right? This iodine is going to react with my water, and then I'm going to form, again, this here would be HI plus OH minus here. And this here is actually this here is not in equilibrium because HI here is a strong acid, right? This guy here is a strong acid. So therefore, if I don't have an equilibrium constant here, if I don't have an equilibrium solution, all I'm going to do is I'm simply just using my mole table, right? And if I'm assuming it's a constant concentration or constant volume here, this is 0.25 molars, which means this guy is 0.25 molars, which is 0.25 molars, which means HI has to be also 0.25 molars here. So all I can do is all I'm doing here is I'm simply just using this here is my strong acid here. So again, Ki here is dissolving into I minus here, and then I minus then reacts with the water here. So Ki here is actually a salt, right? This guy here is a salt. It's an ionic salt produced by a strong base and a strong acid. And let me write down like an equation here. Let me erase this here because we actually don't have to do any math here. This is just some side work here. But if I'm producing potassium iodine and water in a neutralization reaction, I can assume that my K here is going to be my metal for my base here. I can think of this as maybe potassium hydroxide, and HI would be my acid here. So it's a product of these two guys. It's a double displacement reaction, neutralization reaction, and I have hydroiodic acid plus potassium hydroxide would give me my potassium iodide here. And both these guys here I know are strong bases and strong acids, and you can, this here is a strong acid, strong base. So therefore, if I have a strong acid, strong base neutralization, it's going to neutralize, which means like the Ki, the pH of the salt here is going to equal the pH of Ki here is going to equal 7 because it is a strong acid, strong base reaction here. So my ionic salt is neutral in this case. So again, this solution here is correct. You could think of this guy as also kind of like, you can think of this as also like this equation here. Again, I have this HI here and this OH is going to neutralize, right? I have a strong acid here and a strong base here. Both of these guys will neutralize to form a neutral compound as well. So this solution here is correct. It's a good analysis as well.